So let me talk about separability. So fix a field F. If you give me an element in some algebraic extension, I want to define what it means to say that A is separable. So it will be convenient to fix an algebraic closure of F containing K. Just fix an algebraic closure of K, that would be enough. So whatever extension, let's fix an algebraic closure once and for all. And whatever algebraic extension I consider, I'll always consider it to be a sub-extension of F bar. And this doesn't cause any loss of generality, because if you give me any algebraic extension of F, we know that there is some subfield of F bar that is isomorphic to it. So let be an algebraic extension, and I'll always assume that it's inside this fixed algebraic closure, and you take an element. A conjugate of A is a root of the minimal polynomial of A. So it's a brother of A. So let Px be the minimal polynomial. A conjugate, so this is the first definition. A conjugate of A in F bar is a root of Px. So if you give me a number like omega 2 to the 2 pi I over 3, this is a number in some extension of Q, let's say. This is after all a complex number. This is an algebraic number. Its minimal polynomial is x cubed minus 2. So conjugates of this number are 2 to the 1/3, 2 to the 1/3 omega, 2 to the 1/3 omega square. This is an example that we have been carrying with us all along. Yeah. So if you have a minimal polynomial that is of degree d, then this guy can have at most d conjugates. So A has at most d equal to degree p many conjugates. And if it has that many conjugates, then I say that A is separable. Say that A is a separable element if Px, if it has d conjugates. Where d is the degree of the minimal polynomial, i.e. the minimal polynomial, let's call it P sub A, has all distinct roots. Sometimes the word separability is also applied to a polynomial. You say a polynomial is separable if it has all distinct roots. So we are saying that an element is separable if its minimal polynomial is separable. And then an extension is called separable if every element in the big field is separable. Say that. So final definition. Say K over F is separable if each A in K is separable. And the thing is that if you are only interested in characteristic 0, then everything is separable. So the non-separable extensions only appear in these characteristic P situations. So that's going to be the first lemma. Any algebraic extension in characteristic 0 is separable. Also, any extension of any algebraic extension of a finite field is separable. Or of a finite field. So I'm going to only prove this part. So any extension of rational numbers, for example, is separable. So this one actually almost has been proved. So you take f characteristic 0 and you take an algebraic extension and you take an element in K. Let Px be the minimal polynomial. So this is a polynomial in Fx. It's the least degree polynomial that A satisfies. Then we know that this is an irreducible polynomial. Then Px is irreducible. So in particular, it's not a constant. Okay. Now we are trying to say that this polynomial has all distinct roots. But we have this lemma we just proved while looking at finite field, which I have quoted up here, that a polynomial has repeated roots in some extension if and only if there is a common factor between the polynomial and its derivative. So if Px has repeated roots in some extension, then GCD of Px and P prime x is not equal to 1. Means what? Means it has they have a common factor other than 1. But the only factor of Px is 1 and Px. But Px is irreducible, you see. So the only factor up to unit, of course, of Px up to unit is 1 and Px. So what does that mean? That means that this common factor has to be Px. So Px divides P prime x. But then this guy, if it has degree d, the derivative has degree 1 less. In characteristic 0, that's true certainly. At any rate, it has degree strictly less than the degree of the polynomial that you started with. So if you divide a polynomial of lower degree, then this derivative has to be just 0. But in characteristic 0, if the derivative is 0, you can check easily that the polynomial has to be a constant. This you know from calculus, but it just follows formally. This implies in characteristic 0, this is where you need characteristic 0, by the way. It follows that Px is a constant, which is a contradiction, because it's an irreducible polynomial. So in particular, it's not a constant. Yeah, and this is the step that might fail in characteristic P. Okay, so at any rate, if you're only interested in characteristic 0 extensions, then all finite and or even algebraic extensions are separable. So we only need a certain consequence of this separability if you are interested only in characteristic zero extension. So that's all I'm going to actually prove, and I'm going to quote some of the other results, but skip over the proofs. So this, I think, begs the question that we should at least show some example of non-separable extension, and the standard example is, so it has to be characteristic P, and then finite field won't do. So the next candidate is you take one variable rational functions over a finite field. So let that be your base field. And over that, you take the extension obtained by, which is roughly written as t to the 1 over p, meaning add a pth root of this variable. How does that work formally? What I really mean is you put this inside fx mod x to the p minus t. So verify that this thing is an irreducible polynomial. This is in fx. T is already in f, by the way. So f is the ring of rational functions with coefficients in fp. So you take this polynomial, verify that this is a irreducible polynomial. So this guy k is an extension of f. And what it is you're setting x to the p minus t equal to 0. So the image of x in k is the pth root of t. So that's why we write it like this, roughly. So this is your f anyway, and up here you have fx mod x to the p minus t. That's the extension you're looking at. Now this polynomial was irreducible down here, but up here, when you impose this condition, then it splits as a, so let alpha be the image of x in k. Then you can check, then alpha to the p is x to the p, which is t in k. So this polynomial becomes x to the p minus alpha to the p in k, in kx, which now factors as x minus alpha to the p. Because you are in characteristic p, we have this amazing formula, right? So p is odd, I suppose. Okay. So what that means is that the only root of this equation in k is alpha. So it has p times repeated roots. And this is what a typical non-separable extension looks like, because of, so they exist only because of this phenomenon, basically. So alpha has only one conjugate itself. So this polynomial was irreducible down here, but now up here it just becomes a pth power. So it has, all roots are repeated, so there's one distinct root only. And you can check the derivative of this thing is p x to the p minus 1. And I'm differentiating with respect to x, so t differentiates to 0. But this is just 0. But that does not mean that the polynomial is a constant. So that's where this argument fails, you see. In characteristic 0, the derivative 0 means that the polynomial is a constant, but not here. Okay, so this is a typical non-separable extension. So we'll prove a few things about, maybe a couple of things about separable extensions next time.